next talk is on optimal average case reductions to sparse PCA from weak assumptions to strong hardness by Matthew Brennan.
Hi, so this is joint work with my advisor, Guy Resler. So I'll be talking about average case reductions from planning clique to sparse PCA. So the focus of this talk will be on the sparse PCA detection problem, where you observe NIID samples, which under the null hypothesis are from a standard D-dimensional Gaussian, and from the alternative hypothesis are from a D-dimensional Gaussian spiked in a sparse direction V. Throughout this talk, V will denote the sparse direction, N will denote the number of samples, D the dimension, K the sparsity, and always we will view V as uniformly at random chosen from a natural distribution, like the set of all unit vectors with non-zero entries plus or minus 1 over root K. Also, K will always be thought of as much smaller than root D. So this model has been very well studied, and it's known to be information theoretically impossible if the level of signal theta is much smaller than square root K log D over N. On the other hand, polynomial time algorithms only begin to work when theta is at least square root of K squared over N. So there's this K to K squared gap. One remark I'll make is that generally people consider the estimation version of this problem, and for us, detection implies hardness of estimation up to L2 error theta. So when you try to show lower bounds against polynomial time algorithms, you need to make some sort of complexity assumption. So the complexity assumption we'll focus on is planted clique. So the planted clique problem, in the planted clique problem, you observe a graph G with n nodes, and the task is to determine whether or not it's sampled from an Erdős-Rényi random graph with edge density half, or one where there's been a K clique planted uniformly at random in this graph. And even though the planted clique becomes the largest clique in the graph as soon as K exceeds 2 log n, it's only when K exceeds about root n that polynomial time algorithms for planted clique begin to work. So the planted clique conjecture is that this is optimal, that you need K at least root n for PC to be solvable. So just to state very concretely the goal of this talk is we're going to be focusing on reductions which begin with a hard instance of planted clique, so one with K smaller than square root n, and map to an instance of sparse PCA just below the conjectured computational limit of square root of K squared over n. And these reductions have to work in polynomial time and need to map the corresponding hypotheses to one another within little o of 1 total variation distance. Why this setup? Because total variation distance will allow any test for sparse PCA with type 1 plus 2 error epsilon to correspond to 1 with that same error for planted clique. So there have been a number of previous reductions from planted clique to sparse PCA, beginning with a Colt 2013 paper of Berthet and Rigolet, and with several others following after. And all of these reductions either map to, they show hardness for algorithms that run in polynomial time and are robust to the noise distribution of the model, so not quite the spike covariance model that we're considering here. Or they show lower bounds at a suboptimal rate of theta is K squared over n rather than square root of that. So our first main result is a reduction which resolves both of these issues simultaneously, mapping to the spike covariance model and at the optimal rate of square root of K squared over n. So this is just a brief overview of how the reduction works. We begin with planted clique, and then we apply an average case gadget that asymmetrizes the adjacency matrix in Planck's diagonal terms. We then have another gadget to Gaussianize this data matrix. And the key step is to sample a rotation matrix from the Haar measure on the orthogonal group and rotate each of the rows of the data matrix by this rotation matrix. And this spreads the signal out and actually exactly maps the distribution of this Gaussianized planted clique to the spiked covariance model. And then we just have some post-processing steps with subsampling and padding. So if you analyze this reduction, you can show that the signal level that we arrive at is big K over square root of n, where K and n are the parameters of the planted clique instance, times the optimal rate for sparse PCA. So basically what this means is that if we can start with an instance that's about K is root n, then we've shown exactly the result we want. But what if you ask the further question that we start with some suboptimal instance of planted clique? So maybe K is n to the 1/3. Then if you plug this into the rate here, turns out you show nothing beyond the information theoretic limit, so no non-trivial hardness. So the second question we try to answer is, what if we just are willing to only assume the Planck-Clique conjecture for some incredibly small size of Planck cliques, so like maybe polylog n or something like that? Can we show any non-trivial hardness? And the answer is yes, and it's based on two observations. So the first observation is that all previous reductions treated the Planck-Clique data matrix as the samples for sparse PCA in one way or another. And this is wrong for several reasons, but it's most obviously seen by noting that the empirical covariance matrix is much more closely aligned with a Planck-Clique instance. So if you scale and shift the empirical covariance matrix of a bunch of sparse PCA samples, you can see that it's equal to like theta root n over k times some block of ones plus a noise matrix with order 1 fluctuations. And note that this looks like a Planck-Clique instance exactly when theta root n over k is approximately 1, which is exactly the optimal rate for sparse PCA. So this gives us our new reduction idea, which is instead mapped to this scaled and shifted covariance matrix, and then from there get to the samples. But this comes with an issue. So the issue is that there are really complex dependencies among the entries of the empirical covariance matrix. And our average case reduction techniques seem to really need independence among entries of data matrices to map to them. So the way we overcome this is with a random matrix theory result of Bubeck et al. So it turns out under H0, these dependencies disappear if you start with a sufficiently small Planck-Clique instance. And under H1, you can maneuver with this theorem to show that actually the dependencies become Gaussian in nature. And so in particular, you can decompose the empirical covariance matrix into the sum of 4 Gaussian terms. And the key observation is that these 4 terms have meaning. The first is just noise, but the second 2 are actually very, very weak instances of sparse PCA themselves. And then the third one is just an elevated submatrix. So putting this all together, we can arrive at our second main reduction, which first we have a gadget to clone Planck-Clique and have 3 instances of Planck-Clique. And then we map them to each of the terms that appeared in the previous structure theorem. So the first one is, the first problem is a Gaussianized version of Planck-Clique, which we can map to just like we did in the random rotations reduction from earlier. And then the second 2 are very weak instances of sparse PCA. So we can actually take the previous reduction and plug that in to map to the second 2 problems. But the thing though is that these are so weak that they're below actually the mapping to something below the optimal rate is totally fine because all of the signals captured in the first problem. Then just add up all of these terms and you arrive at something which under both H0 and H1 is distributed as the empirical covariance matrix of the spike covariance model. And then now our final step is to sample a random orthogonal matrix from the Hard measure and then take its top rows and then rotate the empirical covariance matrix by this rotation, like these top rows of a rotation matrix. And you can show that this exactly samples the distribution we want. So putting it all together in a theorem, we show tight hardness for sparse PCA assuming k is much smaller than square root of n in the Planck-Clique conjecture. And that's it. Thank you.
We have time for a couple of questions.
So the random matrix theory results analyzes when a GOE matrix converges to a Wishart matrix. So for a Wishart matrix, you have 2 parameters. You have the dimension of the samples, and then you also have the actual dimension. Sorry, the number of samples and the dimension. And if the number of samples is sufficiently high, then you're adding up a bunch of independent terms, and it eventually Gaussianizes to a GOE matrix. And they characterize that rate. So currently, no. Like, we don't know of a reduction, but I think it should be closely related to this random matrix result. Yeah. Yeah, but we don't have one.
let's thank the speaker again. He's going to give the next talk as well.